Right, let's make a start, shall we? Okay. Good afternoon, everyone. In today's class, we're going to continue on from where I left off last week on certainty equivalent valuation. Okay, so that's yeah, I know you're all excited about tomorrow's test, but I did a test run. I finished it in 72 seconds, full marks, but that doesn't mean anything, isn't it? Because I'm the one who set the test, but yeah. So focus on the more important stuff, okay? The more important stuff are today's workshop and indeed your tutorial questions. I have already uploaded the suggested solution for this week's tutorial, tutorial 2, but I've also said that you do not need tutorial 3 to, the third tutorial to handle tomorrow's test. To say otherwise, it will be a very horribly difficult test, okay? So you don't need to go to that extent, okay? So something simple and basic, okay? Right, let's get back to focus, okay? It's on certainty equivalent value. And as I've said towards the end of last week's class, the purpose of certainty equivalent valuation is this idea of disentangling the adjustment for risk and the adjustment for the time value of money. So last week I've also remembered that I've given you a few examples on why the treatment for risk is a lot more trickier than the treatment for time value. Because you see, with time value changes with time in a very predictable manner. 1 plus r, 1 plus r squared, 1 plus r cubed to the power 4 to the power 5, etc., etc. Okay? So the time value part of cash flow is easy, is predictable. There's common understanding on what it is, but it is the risk part that's a bit more tricky. So certainty equivalent valuation is a means of trying to have separate adjustments for risk and time. And I've also given you 2 sets of examples on why the treatment for risk is a lot less straightforward than the treatment for time value. And the first example, or the easiest example, would be a time series example where you consider a given project. Now, realistically, most big scale projects, the way that risk evolves is not just one straight line. You would often have a startup phase of the project where it's anywhere between 3 to 5 years, where it's a lot more riskier than the remaining years of the project. And examples that I've given you last week include things like R&D and experiments for pharmaceutical, biotech, and IT companies. And indeed, even for mining companies or oil companies, excavation and drilling is a lot more riskier than the actual extraction of the oil or the iron ore, etc., etc. So for any given project during the course of its life, risk doesn't evolve in a linear fashion. It is more realistically described by sort of 2 stages. The initial stage is always a lot more riskier than the eventual stage of the project. So that's one example where you need separate treatments for risk and time value. Now the other example that I've given you is sort of a more cross-sectional example where for a given firm, you could be faced with a series of projects, but some projects are a lot more riskier than the sort of projects you normally undertake in your line of business, whereas other projects are less risky than the sort of projects you take in your normal line of business. So if you were to unconditionally apply an overall cost of capital across all those projects, what I said last week is that you'll be biasing in favor of those above average risk projects because you are using a discount rate, a cost of capital that is not as harsh as it should be for those above average risk projects. And conversely, if you apply the same cost of capital to those below average risk projects, you'll be biasing against those projects, those below average risk projects, because the discount rate that you apply is a lot harsher than what is being justified. Okay, so problems to do with the nature of risk, whether cross-sectional or whether time series-wise, is why we need this idea of certainty equivalent is useful. It disentangles the adjustment for time value and the adjustment for risk. Okay, so that's what we did towards the end of last week's class. And indeed, that's what this is trying to do. So, but in terms of the concept, of what certainty equivalent is trying to do, I mean, it's surprisingly simple. So let's throw in some numbers since it's the start of Thursday afternoon. If you are faced with a risky cash flow in 1 year's time that you expect to receive in 1 year's time, okay, it's a risky cash flow of $100. You may be thinking about the $100 that you're about to receive in 1 year's time, and because it's risky, there's a small chance that you might not actually get it. So maybe it's, during the course of the next year, some nights you might not sleep well, worrying about it and things like that. If you say, oh, $100 is trivial, or just add an M behind it, or 100 million, okay? So you can play around that in your mind. But equivalently, you could then say, okay, I would be indifferent between receiving $100 in 1 year's time, but there's a small chance that I might not get anything. Or if I were to instead say, I'm willing to accept $92, knowing very well that I will get that money in 1 year's time. Now be careful here, we're not talking about discounting. The cash flow, the amount that you're about to receive is still in 1 year's time, whether it is 100 or 92. The only difference is that the 92 is the equivalent amount that you will receive with certainty, hence the name certainty equivalent, as opposed to a $100 risky cash flow with a small chance that you might not receive it. Okay? So you are at a boundary where you're indifferent between receiving a $100 risky cash flow with a small chance that you might not get it versus getting $92 in 1 year's time with certainty. Okay, so that's the idea of certainty equivalent. Now, so the concept itself is pretty straightforward. And before we move on, just to make sure that you have a good feel for this, the difference between those two numbers, and I just sort of made up those two numbers, is $8. Can anybody give a sort of more basic description of what that $8 could represent, just so we can then move on and say, oh, that makes sense. That's one way of looking at it. Anyone? How can we view that $8 from 100 to 92? How would you describe it in more layman's terms, so to speak?
Well, that would imply that if the total discount rate, then 8% is, and 8% component is for the uncertainty, then it would have to be some extra component from those.
Yeah, I did notice you last week. You always give the more in-depth version than what I'm looking for. Something more layman's term, please. Then everyday life.
$8 is the cost of risk.
Close enough. I'm more thinking like an insurance premium. Yeah, some sort of insurance premium to make you sleep better at night. So you pay the $8, get it with certainty. Okay, so something along those lines. Okay, yeah. So that's the idea of what certainty equivalent is trying to do. And in terms of what I'm, this is a lot brighter than. Always dealing with equipment. And in terms of what I meant to cover in last week's class, this alpha T is what we call the certainty equivalent factor. So it is the number you attach to the risky cash flow, reducing it from 100 to 92, for example. Okay, so it is a number that is less than 1 that would shrink a risky cash flow and transforming it into a riskless equivalent from 100 to 92. So it has to be a number that is less than 1. Okay, we're shrinking a risky cash flow to a riskless equivalent. Okay, so it's a number less than 1. And it seems from this expression here in your formula sheet that the way that we oh, come on. Okay, the way that we are trying to calculate this is to take the ratio of two discount rates. Now, RF is something that you should have seen from your prerequisite. It's the risk-free rate. So F stands for free, so risk-free rate. And your KO will be your overall cost of capital. Okay, and because your risk-free rate is less than your overall cost of capital, this ratio, whether it is to the power 1, 2, 3, or 4, must be a number less than 1. It would always be less than 1. Okay, so that's the mechanics of it. Now, how do we arrive at this number in the first place? I guess that's always the more important part of it, the concept behind all these different expressions. Okay, the logic is simple enough. Assuming that we're doing a very simple discounting of a risky cash flow at year T, whatever that is, okay, it doesn't really matter. 1 year's time, 2 years' time, it doesn't really matter because we're scaling it to the power T, okay? So this is how we go about discounting a risky cash flow. Now, if I were to write out the certainty equivalent version of this calculation, what would that expression look like? So you see, I'm going to do two things. Number one, I'm going to try to transform this, to write another notation that is the riskless certainty equivalent version of the risky cash flow. Okay? And so this is the certainty equivalent value, the riskless version of the risky cash flow. Now, if I were to discount the riskless version of this cash flow that is still positioned at time t back, the discount rate that I would use will no longer be a risk-adjusted overall cost of capital. I would only need to use a discount rate that takes into account the time value of money. So in this case, it will simply be the risk-free rate. Okay, whatever the risk-free rate is, that is what I'll use to discount this riskless cash flow. Now, and then the next thing that whoever the person who came up with this idea, what he did is say, okay, how do I actually get the riskless certainty equivalent value in the first place? So I invent a notation that is called alpha t, the certainty equivalent factor, and I multiply it to the risky cash flow. Okay. Okay. So instead of writing it as CEVT, which is whatever the riskless amount is, how I actually go about to obtain this amount is simply to multiply the risky cash flow by the factor, the alpha factor, which is the certainty equivalent factor, a number less than 1. Okay? So this is the same as CEV, and because of that, the discount rate that I use at the bottom is still the risk-free rate. I'm just trying to extract from the risky cash flow a riskless equivalent of it. Yeah, that's all. So it's a simple logic to say, oh, okay, I want a riskless version, which is this expression, and how do I express the riskless cash flow in terms of the risky cash flow? I'm applying an alpha to reduce it, to reduce the risky cash flow to a riskless cash flow. So the logic seems simple enough. Now, if you have a look at the first and third expression, what can you immediately do? You notice that the risky cash flow is in both of them, and because this is the same as this, which is the same as this, so if I cancel this two, what am I left with? The ratio of the risk-free rate to the risky rate, so 1 plus RF divided by 1 plus KO, both raised to the power T for whatever the certainty equivalent factor, the year that the certainty equivalent factor applies to. So if we're applying a certainty equivalent factor to the first year, so this is just the ratio of 1 plus RF over 1 plus KO. If it's the second year, it's just the first year square, and so on and so forth. Okay. Now this is exactly the same as I hope you don't have to ask this question, but this is exactly the same as this. Yeah. If you bracket the power term, it applies to both the numerator and denominator. Don't believe me, ask your calculator. Okay, you can throw in some numbers and it'll give you that answer. Okay. So that is how this expression comes about. Okay, it's from this simple story here to say that, oh, that's how we get the certainty equivalent factor. Okay. So that's the main crux of what the item is, so how we do it. And in terms of a simple numerical calculation, so I've made up some numbers there. If we were to conduct an NPV calculation as per normal, so we got some initial outlay, which is 100,000, first year's cash flow 50,000, second year 40,000, third year 50,000, and if we apply a risky overall cost of capital of 12%, we get about 12120, so that's the NPV. Now, if we were to work out the NPV under certainty equivalent, if we apply this alpha t, and just so we know where this comes from, the risk-free rate is 8%, so I gave you that number, and the risky rate is 12%. So the ratio of the two, for the first year, it's just 1.08 divided by 1.12. And for the second year, it's just the first year square. And for the third year, it's just the first year to the power 3, and so on and so forth. Okay? So you have these three sets of numbers. Now, if you apply the three alphas for the first year, second year, and third year to the three risky cash flows, 50,000, 40,000, and 50,000, and if you work through the calculation using the certainty equivalent channel, remember to discount by the risk-free rate, you don't just end up with a number that's very close. You actually end up with a number that is exactly the same. Now, if you work through this numerical example, you might actually get you will have the two NPVs that's slightly different. That is probably because you did some rounding errors here, because your alpha is not exactly, your first alpha is not exactly 0.9643. It's 0.9643 something something. Okay, so if there's to be any discrepancy, it's just rounding error. But conceptually, those two numbers, they are exactly the same. And I'll show you why they're exactly the same. Okay? Let's focus on the first year's cash flow. Okay? Let's focus on what we're actually doing when we apply the certainty equivalent factor the way that we did according to this expression, the way that most textbooks would have you do. Okay? And I'll just do it for the first year's cash flow. If you can see it for the first year's cash flow, you see it for the entire project. Okay? Okay. For the first year's cash flow is 50,000. Now I know the overall cost of capital is 12%, but there's a reason why I leave it as 1 plus KO, okay? And you'll see it soon enough. Now, if I were to then follow through to get the certainty equivalent version of this, what would that be? Okay. Good, some of you have already picked this up, okay? So if I were to get the riskless version, I have to apply the certainty equivalent factor to 50,000. Now when I apply that, it becomes riskless. When it becomes riskless, I have to apply a riskless discount rate, okay? So that's why it's 1 plus RF. But hang on a minute, what actually is alpha 1? Alpha 1 is simply 1 plus RF divided by 1 plus KO, multiplied by the same risky expected cash flow in the first year. Now if you look at this, what does this expression simply become? Oh, sorry. Yeah, that's right. Okay, it's a mistake here that follows through here, okay? So it's a 1 plus RF in the denominator following on from here. If I were to cancel this and try to simplify this expression, you'll notice that the denominator cancels with this. Now if this cancels, what do you end up with? You end up with 50,000 divided by 1 plus KO, which takes you back to this guy. So if you, I guess my point is, if you apply the estimation of your certainty equivalent factors the way that most textbooks would have you do, you're doing one whole circle, ending up with the exact same number as before, as this calculation shows you. Because in terms of the algebra, the simple algebra, you see that it cancels off to give you exactly the same as before. Okay? So what I'm trying to show you with this topic on certainty equivalent are two things. Number one, the idea itself is good. The disentangling of risk and time is important because of the examples that I've just discussed with you. Cross-sectionally, we have projects of some may be more risky, some are normal risk, the sort of projects we normally undertake, some are less risky. So if you were to apply the same overall cost of capital on all those projects, you have biases. And indeed, even for a given project, if the risk of that project, the way that it evolves through time, is by some sort of two-stage process, then you know that risk doesn't increase proportionately with time. Time value would always increase proportionally with time, but not risk. So the idea of having separate treatments for time and risk is nice. The treatment for time value can always be administered in the denominator as a 1 plus RF 1 plus RF square cube to the power 4, etc., because time value changes proportionally with time. But risk doesn't. So if we can administer risk adjustments directly on the cash flows, it gives us that flexibility. So the idea itself is good. But what I've also shown you here is that if you do it the normal way or the textbook way, it is not wrong, but it is a futile exercise. You don't add any additional value to NPV. Yeah, it's just as this example shows you. Okay, but of course you could always calculate other values of alpha and manually tilt up a bit, down a bit, or even do sensitivity analysis with the alphas themselves and things like that. Okay, so the idea is good. The problem that it's trying to address is good, but have an awareness that if you do it the textbook way, it's not wrong. It's just futile. It goes back to NPV. Okay? So that's the main message that I'm trying to have us aware of. And that is something that we will use to continue into today's workshop, where we try to apply certainty equivalent to address a project whose risk is described by 2 different stages. Okay? So that takes us into today's workshop. Okay? So I'll just quickly switch slides here. Okay. So the learning objectives for today's class is to apply CEV to evaluate a 2-stage project, where it's this more realistically described by risk that doesn't increase proportionally with time. See, for most mining projects, the first few years are always a lot more dangerous than the remaining years, because you get accidents are more likely to happen, for example. Okay, so that's why it does add a bit of value to just a very simplistic straight line NPV analysis. Okay, and after that I can use that to introduce you into real options in project evaluation, and indeed the last part or the bulk of today's class, which is on trying to use decision trees to analyze NPV, to perform NPV analysis under different scenarios. Okay, so that's and that will take us to the rest of today's class. Okay. So I'll go straight into this example, and indeed, if you got even just half, because I know you're doing other subjects and you've got other projects and tests, even if you grasp, say, 60% of last week's class, I hope that one of the things you managed to get is the fact that drawing simple pictures actually helps guide you in your calculations. So that's something that does come out more thoroughly in today's workshop. Okay, so we're going to draw apparently more sophisticated pictures, but they're within the grasp of what we can do. Okay, so it's a simple scenario type pictures, but more importantly, how do we actually use those pictures to guide us in the calculation? The calculation themselves are, hopefully you would see this a few days before the exam, but the calculation themselves, by the time you reach that stage, they are actually secondary. The most important, difficult thing is to actually have a blueprint that accurately reflects the details of this project. Once you have that, you can actually use that picture to guide you in terms of what are the calculations you need to do. Okay. Now, and to further motivate us on this, I'll just not skip, but I'll have you have a look at the very last slide. If you manage to print out your notes, now have a look at the very last slide here. This one. Okay, so this is the monster. So I'll use the word quite literally, the monster that's waiting for us at the end of today's workshop. So you take one look at this and you say, get me out of here, or dear mother of God, what the hell is it? So you look at this expression and you say, oh, there's no way that I'm able to understand this. Okay? So I want you to have to try to remember what's going through your mind now, and then towards the end of the workshop, have a look at this again, and hopefully most of you would say, oh gee, that wasn't too bad. Okay? Because of the picture. Okay? So keep that in mind. Right, let's forget about that for the moment. Go back to this. Okay, so let's start with this a more realistic 2-stage project. Okay, so I'll give you some time to read through this if you haven't. And again, to reiterate, the most important thing is to try to get a reasonable illustration of the key details of this project. So as you read through this, I don't know, of course, different students have different, they pick up different information. Like for me, when I was learning all this, the first thing that I always pick up is, how long is this project? Because the length of it gives me a sense of time, and time gives me a sense of what I need to do when I apply annuity formulas. How many cash flows do I need to shift? Okay. So with this project, anyone like to start us off with a simple question? What's the relevant time horizon to analyze this project? I just want a simple answer. It's a very simple question on the total time. Not a trick question. There's no trick questions with me, or indeed tomorrow's test. Anyone? What's the total time frame? Second line? Oh, you don't have your notes. Yeah. 20 years? Close? 15? No. The initial stage would be what? What would be the first, okay, if you were to describe this project, what would be the first meaningful, the first stage, so to speak? It has to be? No, 5 years is actually the second. Even before that, 2 years. Because after 2 years, we're going to know, geez, this is a complete waste of money. Have we actually found something on the ground? So that's the 2-year period where we actually do our geographical surveys, our excavation to say, wow, there really is something. Oh, it's not copper, it's gold. Gee, I'm rich, and things like that, okay? So 2 years is a time where we are then able to decide, yes, there's something underground, let's start digging. Okay, so the initial stage has to be 2 years of excavation, and after 2 years, we then make a decision. Is this, should we go ahead with this? Or should we do nothing because there's actually nothing underground? Okay? So the initial stage has to be 2 years, and then the next one would have to be 5 years, because the first 5 years, if we do decide to if we do decide to carry out this project, the first 5 years will be more dangerous than the remaining 15 years. Okay, so in your mind, you'll be thinking, okay, 0 to 2, and then 2 to not 5, 2 to 7, okay, 2 plus 5 is 7. Okay, from year 2, we said, yes, go ahead, but the first 5 years is difficult. So from year 2 to year 5. And then after that, from year 7 to year 22. Very good. And indeed, that is the most important part of the diagram, that actual marking of the key dates, the key years on that timeline. Good, okay. So let me, give me some time to draw out the picture. Okay. I'm well aware of, not just for me, but even for you, it's not easy to draw a nice picture, perfect type diagrams, but indeed this is something that really gets you into the crux of the problem that you're addressing, whether for the exam, for the assignment, or indeed later on if you do have to apply all of these things, okay? So it gets you into the details of this. That's why, but I've also adopted a more balanced approach. So in the on DSO, I don't know whether, I hope most of you got this. 2 weeks ago, I've uploaded a sort of more nicely drawn slide. That's for the last example of today's workshop. So with one example, I'll do hand-drawn, and for the second one, you know, you've got a nice picture, we'll just fill in the details, okay? What I used to do in the past is to give students all these nice pictures, and then what I realized is when I mark the exam, all their pictures are wrong, because they don't know how to draw. Because they're used to me giving them nice pictures and things like that. So I have adopted a more balanced approach for today, okay? In terms of the labeling, I'm not that particular because eventually, for all intent and purposes, this is for your own understanding and calculation, okay? So we have here a decision on whether or not to go ahead with this whole thing, to outlay a certain amount of money to start excavating for the next 2 years to see whether it's worth, whether there's actually anything underground. So the initial excavation stage of 2 years has with it an initial outlay of $250,000. And then if we do decide to excavate after 2 years, two things are going to happen. It's either yes or no. Either we find something, so yes, or we find nothing. So if we find nothing, what can you say about this part of the graph, this particular scenario? If I go down here, what happens? Yeah, exactly, nothing happens. So move on to other things, okay? So that's why there's nothing to do here, okay? Now, if we do find something, then the story goes on. We're going to outlay a further $2 million to start up this mine, and then we're going to have a series of cash flows for the next 20 years. However, there's another marking here. I probably should shift this a bit back. Says here, okay. Sorry, this is not 5. This is 7, okay. The initial 5 years of this project is a lot more riskier than the remaining 15 years of this project, okay. So the gap between 22 and 7 is 15 years. And the gap between 2 and 7 is 5 years. Okay, so that's the sort of time frame that we need to have an awareness of. Okay, so this picture is almost complete. I mean, the rest of it is just to fill in the specific details. So I mean, the most obvious detail that I can fill in is the fact that if I do decide to go ahead with exploring whether there's any copper underground, I need to pay an upfront excavation cost of $250,000. Okay, so negative $250,000. So that's the information on the first line that I would put into this picture. What will be what other sort of more obvious information can I begin to incorporate to decorate this picture? Because the numbers guide us in the calculation. What will be another set of numbers? The $2 million startup costs, if we do decide to go ahead with this project. Now, if I were to write that number in this picture, where would that number be? For example, is that number here? Here? Somewhere here. Because if we do decide to go ahead with this project, we have to outlay $2 million. Okay? Okay. So this is something that we will outlay in 2 years' time if we find something underground and this project is a go-ahead. What's the chance of that happening in terms of the chance of me going up versus going down? There's a 60% chance that something's going to happen, and so I'm able to write the probability values to the two alternative states. There's a 60% chance of 3 over 5, which is 0.6. There's something that we do manage to find something. And if that's the case, we pay the initial outlay and we start up this project. There's a 40% chance that we find nothing, and if we find nothing, too bad. And we don't really have to worry about the rest of this line, okay? Because no cash flows whatsoever. We're almost there. What else? If we do find something, we're going to generate an expected net cash flow of $500,000 per year for each of the next 20 years. Okay? So you can write $500,000, $500,000 for the next 20 years. Okay? And that is all. Basically, that's it in terms of the key details that we need to put into this project. These are the cash flows, the initial outlay, the chance, the probability that we do find something and we execute all this, initial excavation costs, etc., etc. But most importantly, and please allow me to stress this, the time markings, 0, 2, 7, and 22. Okay, so these are the meaningful markings the milestones of this project, so to speak. Okay. Now you might not believe this, but as far as the difficulty goes, if you can draw this picture, more than half the work is already done. Because once you see this picture, the calculation becomes a lot easier to generate for yourself. Okay. Yeah. Now, there is a bit more details in terms of the discount rate that is used. Okay, because of the fact that the first 5 years of the mining operation is believed to be a lot more riskier than the remaining 15 years. In the initial NPV calculation, it was proposed that, okay, we shouldn't actually use 15% KO, which is the overall cost of capital that we normally do. We normally use 15% for all our projects, but because of the riskiness of this project for the first 5 years, it is being proposed to us that we should actually use a much harsher discount rate of 30%. Okay, so if we were to use 30% to try to discount the cash flows associated with this picture, what would the NPV be? Okay, so let's do that calculation, or write out the equation for that calculation and see what it looks like. Okay, shouldn't be too difficult, but in any case, I'll do it in a few steps for you. Okay. So how do we calculate the NPV of this under the scenario of using an overall cost of capital of 30%? Okay. What would the calculation look like? Yeah, that is part of the calculation. So, which is what I'm going to do now. Now, the thing that I always write up first is the initial outlay at the very beginning, because that's the easiest one. It's just a lump sum sitting at time zero, so once I write that out, I know that at least I've done something right. Okay, and the rest of it follows, okay? So if I do this, if I trace it up to here, now I know that there's two scenarios, either going up or going down. Now, as far as the calculation goes, this part of the diagram is completely irrelevant to me. Yep, sorry? What was your question again? The 2 million? Yep. No. Line 2, 20 years. Yes. But as far as these markings are concerned, it's correct because it's from 2 to 22. That's 20 years. Okay? Yep, sure. Now if we, where was I? Okay, now we're at this stage. Now if we go down this path, if we try to incorporate this part of the diagram in our calculation, there's no need to do anything because cash flows or net cash flows are all zero. So you multiply 40% by 0 is nothing. Okay, so we don't have to worry about this part. But it is the top part that we need to worry about. So how would I do the calculation to complete my NPV number, taking into account this part of the diagram? Okay. It's a 60% chance of whatever in the bracket is going to happen. And whatever in the bracket is assuming that the project is a go-ahead. Okay? And we attach a weight of 60% or 3/5 to that set of numbers if the project is undertaken. Okay? So that's the best way to think about it. Okay? We attach a weight of 60% probability to whatever the cash flows that that the project generates or whatever the cash flows the project involves within this bracket. Okay? And what would be, just to make sure that most of us, sorry, with this bracket here, what would be the first simple cash flow that I can include that the project involves? Minus 2 million. That's the easiest. Before you start getting money in, you have to initial outlay. Okay, so that's the easiest. Yeah. Okay, like I said, I always like to do the easiest one first because I know at least I got something right. So the first thing that the project would involve is an initial outlay of 2 million. So I can always write that in. Okay. Very simple. Okay, just 2 million. Of course, make sure you know that M stands for million. Okay. And I guess the risk with using all these different notations is that make sure that if you use millions, all your numbers are in millions. Because with, for example, with the net cash flow of $500,000, you do not want to write 500K as part of a calculation. If you write 500K, when you press your calculator, you might press 500, and with this 2 million, you might press -2. That means that your answers are all skewed, because your -2 is actually 2,000K comparing to the 500K. Okay, so have an awareness of the units of measurement in your own calculation. Okay, so that's the first thing I'll say. Now, after writing down 2 million, what will be the rest of the calculation? Well, it's simple. It's just the present value of a stream of 20 years set of cash flows. It's an annuity, $500,000 per year for the next 20 years. So you immediately think of the annuity formula. Okay, so the annuity formula is what you would use. So it's a $500,000, 1 minus 1 over 1 plus KO to the power of T. So in this case, it's 20, and then divided by KO, which is 0.3. Okay, you don't have to write it the way that I did, but it's the annuity formula for a stream of $500,000 cash flows for the next 20 years, doing it in one shot, okay, with this. Now, if I would, this would give me the present value, the total present value of a stream of 20 cash flows of $500,000 each, the net cash flow for each of the next 20 years. And if you ask your calculator, this will give you a number. I'm not interested in that number. I'm more interested in the following. In this picture, anyone, where would that number be sitting at? Very good. I was already expecting that, okay? That's how high expectations I have of you. It's sitting at year 2. Because what you've done is that you've collected this stream of 20 years of $500,000 cash flows. You collect it as a batch. And that number is not sitting at time 0. It is sitting at time 2. Why? Because the first $500,000 cash flow starts at which year? The project starts in 2 years' time. But if we do start this project, when will the first $500,000 cash flow come in? Which year? 3rd year. And then 4th year, 5th year, and then year 22. So when we apply the annuity to discount everything back, it always lands one period before. So if the first cash flow starts in year 3, the lump sum must be sitting at year 2. But hang on a minute, we're calculating NPV. We're always standing at time 0. So what do we need to do with this calculation to complete this? What do we need to do to complete this calculation? Anyone? That's all you need to do. And the picture guides you in that regard. Okay. The 2 million is sitting in 2 years' time. The rest of this is also sitting in 2 years' time. Okay, so it's actually the entire set of cash flows. You need to pull it back from year 2, the end of year 2, to the end of year 0. Okay, so that's why the divided by 1.3 square applies not just to this, but to the 2 million as well. Because we know from the picture that 2 million is sitting in 2 years' time. Okay. The 1/4 million is sitting at year 0. Okay, so everything's fine. So that's all the calculation that we need to do. Now, if you press the buttons in your calculator correctly, you would arrive at an NPV figure. Now, but there's no guarantee that this is correct, okay, because I worked this out myself, but I've done it twice, so it should be right, okay. Give or take a few thousand, doesn't matter. Okay. Sorry? I'm sorry, I can't hear you at all. Oh, I see. You're talking about the 30% versus 15%. Oh, sorry, I haven't gone into that yet. So that's the second half of this example. Okay, so you see, if we were to unconditionally apply what is being proposed to us to say, wow, the first 5 years is risky, we shouldn't use 15%, we should just use 30% to discount to evaluate this project, what would the outcome be? And then re-evaluate using what we've just did with certainty equivalent. Okay, so that's the second half of this example. I'm just talking about the first half because the calculation is, for some of your peers, not that straightforward, so I have to do it slowly. Yeah. So if we apply a 30% unconditionally to penalize all the net cash flows for the 20-year project, we arrive at a number, give or take a few thousand, negative 371,457. Okay, so it appears that if we do the calculation applying 30%, this project is unacceptable. It's a negative NPV project, so we'll shake our head and say, sorry, no go. We can't do this. Okay. Before continuing on with this project, maybe a small portion of you might have some struggle with why is it 1.3 square? I thought it's 1.3 to the power of 400 or something like that. The picture guides you, okay, and we're going to do this a few times, so if you don't get all of it this time around, there's plenty of chance for you, okay, so don't worry too much. And then if you still can't get it after the workshop, there's the tutorial next week. Still can't get it, there's the assignment. And if you can't do it after the assignment, I don't know, okay, so yeah. So it appears negative, but then we can then go on to the second half of this example, which is the following. Okay, it appears from this calculation that, oh, this project is unacceptable, negative NPV. But I mean, should we actually apply the 30% unconditionally on the entire stream of 20 years cash flow, given that the risk, the additional risk is only for the first 5 years? Okay, so that's the issue. Maybe we should consider using indeed a harsher or a more stringent risk adjustment, but just apply it for the first 5 years and then apply a more normal discount rate of 15% for the remaining 15 years. So maybe that might be a more acceptable approach. And if we do that, what would the NPV figure look like to us? Okay. Yeah. So that's the, I guess, the conceptual flow of this. If we were to use a harsh discount rate just because of additional risk, even though the risk only applies to the first part of the project, it gives us wrong answers. So we try to have a more detailed addressing of the risk of a project in terms of 2 different stages. Okay, so that's the purpose of this example. Now, before moving on, just a quick conceptual check here. If we indeed, okay, say we apply 30%, but just for the first 5 years of the project, and if we can somehow apply a more normal overall cost of capital of 15% on the remaining 15 years of the income stream of this project, what should the NPV be? Regardless of what we do, whether it is NPV or certainty equivalent, relative to this number, what should the revised NPV be? It must be a number that is higher. It has to be a higher number. I don't care what score you get for the prereq, okay, you must at least know that. If you apply a harsher discount rate just for the first 5 years and a lower discount rate for the remaining 15 years, your answer must be larger than this. It has to be. Okay? It has to be a larger number. Yeah. So how do we actually do it? Well, one way of looking at it is, I'll give you this example and then I'll elaborate on the second half of this slide, okay? You could then say, okay, the time adjustment with the 8% risk-free rate, I can apply to the denominator, but I'm able to manipulate the risky cash flows, the first 5 sets of, sorry, the $500,000 net cash flow for the first 5 years, I can apply an alpha T that is harsher, more stringent, smaller values than the alpha T's that are applied for the remaining 15 years of $500,000 net cash flow. Okay, so it is this flexibility of having separate treatments of the risk for the first sets of 5 years cash flow, and then a sort of more normal treatment of risk for the remaining 15 years in the numerator directly, and then discount all of them back with using the risk-free rate. Okay, so that's the idea of it. So I guess if we were to follow the textbook way of doing things in terms of estimating our alphas, your alpha for the first 5 cash flow would simply be the ratio of 1.08 divided by 1.3 to the power 1 to the power 2, 3, 4, 5. Okay, for each of the first 5 cash flows. And then you would switch to a more normal certainty equivalent factor for the remaining 15 years. 1.08 divided by 1.15 to the power 6, 7, 8, 9, 10, up to 20. And then with those riskless cash flows for over the 20-year period, you would then discount it back by 8%, which is the risk-free rate. Okay, so that's one way of looking at it. In terms of the separate treatments for risk directly on the cash flows in the numerator and discounting back for time value using the risk-free rate in the denominator. Okay, so that's the way to do it. That's what the first half of the slide is about, but more interestingly for the second half, it goes back to what I said about if you follow the textbook method blindly, if you apply the ratios, I mean the way that you estimate your alphas based on the ratio of risk-free and risky discount rates scaled by which year that alpha applies to, it is as if you're doing the following. It is as if you're doing NPV, but you apply 30% to discount the first 5 years of cash flow, and then you immediately switch to a 15% overall cost of capital for the remaining 15 years. If you go through with this calculation, I'm pretty sure that you will get a very similar answer to a normal NPV calculation, but using 30% for the first 5 years and 15% for the remaining 15 years, instead of 30% for the whole series of 20 years. Okay, you get exactly the same. You should get exactly the same answer. But it is one thing to say that it's a futile exercise, but this example does show you that because of separate treatments for risk and time value, you can play around with different alpha figures. It doesn't have to be according to this textbook type estimation. Okay, but it shows you the separate treatment of it over time. Okay, now just for the interest of what we're going to look at later on, I think it's worthwhile that we actually do this exercise. So if you can see this, the calculation that I'm going to do, which is the following. We're going to do an NPV calculation similar to this, but the only difference is we're going to use 30% for the first 5 years, and we're going to switch to 15% for the next 15 years of cash flow. So the calculation is going to be a bit more complicated than this. But if you can understand that, then the monster sitting at the end of the workshop suddenly becomes quite easy. And indeed, that would be, if I look through all my 6 workshops, what we're going to do next will be the most difficult numerical example of all of them. So if you can somehow grasp most of it, well, then it's easy on for the next few weeks, okay? Yeah, so we'll try to do that and see how you go with it, then we'll take a short break, okay? So here's the objective, okay? Let me reiterate this. We're going to do this calculation again, but the only difference is we're going to apply 30% for the first 5 years and switch to 15% for the next 15 years. So what does the calculation look like? Well, a bit more complicated than this. This is 30% all the way. Okay, so how do we do it in parts, okay? Yes, that would be the first step. Yeah. And then, yeah. 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 That's not the main worry. The main concern is how do you then shift those things back to zero. That's the one that I like to highlight on. The actual grouping, calculating the present value of a set of 5 cash flows or calculating the present value of a set of 15 cash flows is easy. Most of you can do that. But it's in terms of shifting everything to time zero, that's the one that's a bit tricky. So that's the one that I'm concerned about, not the actual 15 and 5. Okay, so keep that in mind. And if you can handle more than 50, if you can grasp more than 50% of it, well, I'm not saying you can skip the next 3 weeks of class, but the calculations in the next 3 weeks would pale by comparison compared to what we're going to do now. Okay? And even what we're going to do now is not that bad. So have a go. Let's do it together. Okay? I can't have it with me because of obvious space constraint, but you're always able to have this in front of you when you do the calculation. Okay? So far, so good? What's going on? No, nobody's going to say that, okay? This calculation is exactly the same as before. The only difference is, okay, let's go back to basics. You still have to pay $250,000 to excavate for the first 2 years. So that doesn't change. The probabilities are still the same. Whether we find something or not depends on Mother Nature. It's not affected by our choice of discount rate, okay? So this stays the same. The 2 million is still the same. The initial outlay in 2 years' time, if we do execute this project, is still 2 million. So that doesn't change. It is still $500,000 expected net cash flow for each of the 20 years. But the only difference is we're trying to acknowledge the fact that the first set of the cash flows for the first 5 years is a lot riskier than the cash flow for the next 15 years. So what I'm doing here is to apply a harsher discount rate of 30%, but notice that it's only to the power 5, which means that with this, I'm going to take care of the first 5 years. What about the next 15 years? Anyone like to read out? Yes? To the power 15. Good. I don't care where we are in terms of the timeline. If you want to work out the collective present value of a stream of 5 cash flows, if the annuity amount is the same, it's power 5. If I want to work out the collective present value of a stream of 15 cash flows, I don't care where I am, it is power 15, using the relevant overall cost of capital. This I'm not that worried. What I'm worried is the following. This rate component, the remaining 15 years, if I just point to this by itself, can someone tell the class, in this picture, where the heck is that number? We know it's a number. Your calculator will tell you a number. I want the location. I have actually no idea. I need to think, but 7. We got 7, we got 3. This rate expression collects 15 years of cash flow and put it 1 year before. Now, I guess the best way, the correct answer is 7, but that's not as important as why is it 7? I thought it's 210. Why is it 7? For the second stream of cash flow of 15 cash flows, when does that cash flow actually start? Which year? For the second stream? Year 8. Because you see, for the first 5 years, your project starts at year 2. So the first cash flow is year 3, 4, 5, 6, and 7. So that's where the first stage ends. For the second stage, the first cash flow starts not in 7, but in year 8. So when we apply annuity, we push it back to year 7. So if this guy is sitting at year 7, now get things in perspective, negative 2 million, which year is this sitting at? Good. This one? Good. If this one is 7, I want to make sure that as far as whatever's within the bracket is concerned, I want everything on the same timeline, on the same time position. So if 2 million is in year 2, if the second expression is also in year 2, if I want to push the remaining 15 years back to year 2 to align everything together, what would I simply need to do? Anyone? It's 1.15 to the power of? Very good. This would push it from year 7 back to year 2, which means that this answer is aligned with this answer, is aligned with this answer. So far, so good? We're almost there. Hopefully nobody's saying, isn't that more than enough? Almost there. It's not complete yet. Remember, we are asking for an NPV number that is always at time 0. This is 0. Everything that's in this bracket is year 2. So what do we simply need to do? Anyone? 1 plus KO to the power of? Very good. And it applies to this entire expression here. Everything's now at time 2, year 2. We're going to pull it further back to year 0, and that completes our calculation. And there you have it, folks, the most demanding calculation in all of my 6 workshops, which is not too bad, seriously, okay, given the response that I'm getting here is, for sure, if you only get about 50-60% of it, no worries, we're going to do it again later. And then you do it next week, and then in the assignment. If you do it again in the exam, you'll be thinking, oh, gee, thanks, Michael, you're really a godsend, okay? Yeah. No, I divided 2 million by 1 plus 1.3 to the power of 2, because it's in year 2. Yeah. Yeah. Yeah, it doesn't look that way here, but the idea is to exclude it from the bracket. Yeah. Now, this last point here is something that, how to say, let's leave it as an aside here. The reason why I write 1 plus KO here to the power 2, now we know that everything in this bracket is in year 2, and what I'm doing here is to pull it to year 0, take it with this, and work out the revised NPV, which you know must be an answer that is, even if it's not positive, it must be a larger value than our previous calculation. There is an interesting, when I was doing this, because of time constraint, I don't know whether to get into too much detail, so I'll leave this as a rough discussion, but I won't examine you to that extent, okay? But I might ask that as a question. I mean, why do I seem to hesitate when I point to this? Why don't I just write a number here? Now, we are faced with 2 different numbers. One is 30%, the other is 15%. Do you know why I leave it as a KO here? Or I can ask the following, what should this be? 1.3 square or 1.15 square? You see, the 15% is to apply the normal operation of a copper mine, which is fine. Now, we say that the first 5 years are additionally risky because, we don't know what accidents might happen. So we apply 30% for the first 5 years. So we've already addressed, so the 15% and the 30% treatment for the 5 cash flows and the 15 cash flows are clear and explicit. But when we do everything, and when we're at this point wanting to pull everything back from year 2 to year 0, it is not the risk of the project itself, it is the fact that whether or not, what, anyone? For this part of the graph. The risk is not whether the project is going to have an unfortunate accident or not. The risk is actually whether or not anything's there. So it's a different nature of risk altogether. So you might say, oh, if that's the case, whether or not, if we want to address that risk, is it the same risk as the risk of the project in the first 5 years? That's number 1. Number 2, if we want to acknowledge the uncertainty, the fact that we might not find anything underground, we've actually done that already in our calculation. Where? The fact that we might not find anything, we've already addressed that in our calculation here. That's right. The fact that for the benefit of this project, we are only assigning a weight of 0.6. It is not 1. So the fact that we're applying 0.6 means that we are penalizing the cash flows of this project for the fact that we might not find anything with a 40% chance. So whether or not we should use an additional riskier discount rate or whether we should just use 15%, this is where, you have those late night boardroom meetings where they throw things at each other and say, and things like that. So if you ask me, my opinion, I would say it's 15% because the uncertainty of not finding anything has already been absorbed by the fact that we're assigning 0.6. But when I was doing my calculation over the weekend, I didn't think that deep, you see, because, weekend. So I actually applied 30%. But trust me, I'm not going to examine you on this in depth, but this is an issue that you can keep in mind for later on, okay? Now, if I were to use 30%, when I did my calculation for the answer, I used 30%, so 1.3 square. And my answer is the following, okay? Just for completeness, the answer is, I have no idea what the answer is. Oh, okay. Now, if you use 15% instead of my 30%, just a quick revision for tomorrow's test. Anyone? I use 1.3 square to arrive at this answer. If you use 1.15 square, anyone? What answer? What must the answer be relative to this? Yeah, it has to be a slightly larger number. Okay, oh, thank goodness. Okay, so that's the answer. If you use 1.15, you might get a slightly larger number than mine, because I use 1.3. Okay, but that aside, okay. But there you have it. This is a good example to say, okay, if you have a picture in front of you, once you've got the markings correctly set out, the calculation is not that difficult to handle. Okay. We'll take a short break. Okay, say, okay, 10 minutes. Okay, so 5:18 p.m. Okay, we'll restart in 10 minutes time. Okay.
This one here is pulling. This one here is pulling this back to year 2, right? Correct. Year 2, pulling it back to year 2. What if we actually divide this by 2 and this by 7? So we actually put 30% for this, 30% for this, 1.03 to the power 2.
Oh, hang on, why 0.3?
I'm sorry, 3, 1.3
Okay,
to the
okay,
power 2.
okay.
And for this 1.15 to the power of 7, so we're putting.
Yeah, you are doing straight to
Yeah.
0.
So
Yeah.
in that way,
Yeah.
we won't be confused about what to put, whether to use 1.15 or 1.3. In that case, we are actually giving 15% from year 7 to
Yeah,
year 7 to
yeah.
22.
You set everything to 0,
Yeah.
whereas I set everything to 2.
Yeah.
But you still have the same issue when you go past year 2, whether or not it's justifiable for your 15 for your set of 15 years cash flow to go from year 2 to year 0 at 15%, and then for the first 5 years to go back at 30%. You still have that same issue.
No, if I do this, will this be wrong?
No, it is not wrong, but you go back to the same issue that I was trying to discuss in terms of whether this should be 1.15 or 1.3. It's the same issue.
So do we have a certain thing like which rate has to be used on?
No, I would say it is for me to have a clearer, give a clearer response. I may need to put a bit more details into this, because you see. But do you see the point that the 30%, 15% difference is not to do with whether or not we find anything, it's to do with something else. So there's all these issues in play. And I guess the best answer is there is no right answer. But this is something that can be discussed. Yeah. I think that's more important than actually what is an answer.
Michael, thank you. Right now you have said that in your tomorrow's test, there is chances that such kind of question can come. At least one can come. Right now you have this question which you have told in the class right now. In
This
tomorrow's
sort of question.
test,
No.
have you been said? No. It will be a kind of a.
It's only 15 minutes. I took an hour doing it.
Yeah, that's why.
Yeah. No. It won't be that
It
hard.
won't be that hard. That's right.
Yeah. Okay. Don't worry. There may be some calculations, but come on.
At least I think you will give a two question based on theoretical, or all 4 or 5 will be based on
Basic concept, basic
concept,
calculation.
basic calculation.
Yeah.
Okay. NPV is basic calculation.
Something like that.
Capital budgeting, almost.
Okay. Not this
one, not
this.
one.
Yeah, not
I
crazy.
think you said in the class, right? And I think last two
Yeah.
lines during you said that you might get this kind of question in test. So I thought just to confirm it with you that
So
anyway, that is
yeah. Okay.
thanks.
Got a bit of a problem. there was an administrative error, and I've been withdrawn from my course completely. And so I've talked to them, and it's meant to be fixed.
Are you able to access all the material?
That's the, I can't access the material, I can't access the test. It was meant to be fixed by
So I guess the only thing that they didn't do is you need all the slides.
and also I can't access the test.
No, that is not the main. I mean, we can always have flexibility in terms of shifting the 2.5 to your other.
Oh, okay.
Maybe you check your complaints and all that.
So I haven't been around. I just
So, send me an email.
I don't know. I need to know what your email address is.
Not even the first workshop.
Sorry.
Not even the first workshop. My slides, my very first.
Yes, it will be on there.
Just let me know. Then I'll talk to the unit chair and make sure they mark you as unique and
Thank you very much.
but try to fix it up because if you then you'll affect your
Yeah.
you are able to get the first week one or second week.
Yeah, I downloaded the second week one.
Okay, okay. When I reply you, I'll send you all my materials.
Thank you, Mark.
Hopefully
Thanks.
next week. Hopefully next week will be fine. Oh, 0.15 you mean?
50%.
Yeah.
The level success.
They're both acceptable you mean?
Yeah.
No, the point that I'm trying to make there is it's arguable whether they should use.
So if we do the exam paper, there may be two answers.
No, I also say I'm not going to examine into that.
So not mark your final exam. You are not going to mark.
No. I wouldn't examine you to that.
The question will not be.
Yeah, I'm not on that issue. Because if I can't give you an answer, how can I ask you to give me an answer?
Oh yes, and what should we use year 6 to year 20, not the first 5 years?
But the scenario is that it's a story of when you first run a copper mine, you could more
The risk
accident.
is higher.
Yeah. So you say after 5 years, if nothing happens, then it's pretty much smooth. So that's the idea.
There's no argument about use 15% for the first 5 years and the last 50 years use a higher percentage. It's not.
If anything, it will be the other way around. Because you see, startup always a lot more dangerous. When you start digging,
Yes. And about our online test, it's only 15 minutes, so it should be much about understanding Chinese. No?
not
Basic knowledge. In the textbook or something slide.
focus on it.
Focus on the
Slide,
slide.
tutorial questions.
And then there will be a lot of calculations. Simple calculation. So that's why join available from midnight on Friday.
No, Friday noon,
Friday noon.
PM,
Oh, okay.
Saturday noon.
Don't tell me all the questions are going to be the same. Or is there a pool of questions?
It must be a pool because we can do the test with our friends.
Otherwise, confidence
Yes.
is building, tell everyone.
Yes.
So it's a pool of questions.
Yeah, we're not that dumb, so.
Yeah.
can't be. No, it is positive. That much I'm sure.
I don't think so. I believe that when I individualise each part to its component, like obviously that's negative 0.25 million. That's a fair bit negative, that one, isn't it? To get the profitability.
Yeah, but we're talking about 20 sets of this.
Yeah, but the special value annuity category is 15%. You've only 2.8 at 5, and only 5.8 at 15. So 5.8 times 0.5 million is about 2.9 million, and 0.5 times 2.8 is about 1.4 million. So make that 3 million in terms of real cash flow. And then we have to multiply by 3 bits.
No, 4 point something million minus 2 million. 2 point something million times 3 will give you 42.
That's correct, but we also have to discount it by 1.15 for 5 years as well. So then it drags that down to about 2.8 million. Hence, it goes positive, right? It's positive.
Oh, okay, it's positive.
But then, if you have to divide by 1.3 squared, 1.69, it drops into negative territory. It really does. It's not going to calculate it, so how?
No, it has to be neutral.
Alright, yeah.
I did double check, but the most important thing is you do see that if we were to apply that as before, it's not a fair evaluation of the product. So even if this is a negative, it will be a fairer evaluation as opposed to
The other one, yeah.
that is the most important thing. Not to say that it's okay not to get right answers, but I did double check this.
My friend was rubbishing me for doing this for practice and
No, I don't.
very good at these annuity calculations.
I can check, but it'd be easy if I have my calculator.
Yeah,
but,
that's right.
I can make a note to check it again. Try it again, if you can get it immediately, I'll do it and try it.
Sorry, yeah, send me an email with my solution.
You just email me your answer.
Okay, yeah, I'll email you.
Just enroll.
Yeah, just enroll. I don't know about anything.
There is some flexibility to say take the score for tomorrow's test and put it on the next 3 tests. So shift it for your next 3 tests.
If it is possible, then I can do that test next week.
No. What we'll do is what we're likely to do is we'll take the score for that test and we increase the score for your other tests, the total score for your other tests. So you only take 3 tests, it's still 10%.
Okay, so you can do that?
Yeah, but I think you should check with the unit chair. She'll record all this stuff. Check with the unit chair.
Okay.
I should start.
Yeah, just a one. If I want to do that lectures, right? So if I do that first 2 lectures, is it alright for me to do the test tomorrow?
For the first 2 weeks,
Yeah, first 2 weeks.
it should be enough.
Should be enough.
Yeah. But I mean, the calculation will be the easy version of all these calculations. So, yeah. But this I can't be sure. You have to check with the unit.
And so the test tomorrow, that will just be the first 2 weeks, and we'll also do this lecture as well?
It will be this lecture, but not the degree of
Okay,
complexity.
so it's just teaching tree, but obviously not the same crazy decision tree that we've got.
I need to. No, sorry. We'll talk after class.
Right, let's restart the workshop. Settle down. Right, settle down, please. Now I know you're all excited because you say, oh gee, this wasn't too bad, so I'm set for life. Yeah, pretty much. Seriously, if you can grasp most of this, then what I've shown you earlier in terms of the calculation on the very last slide suddenly becomes, you know, it's not something you need to be afraid of, okay? Yeah. But in case you only got about 40% or 50% of this calculation, you get a second chance to do it again towards the end of today's workshop, okay? So by that time, you should be right to show off to Campbell and John Gore next week, okay, in the tutorials. Okay. Right, let's go into real options in capital budgeting. So, I mean, a lot of what we do, what we've done in terms of looking at different scenarios is already leading into decision tree analysis. Strictly speaking, this is not a decision tree because what we've done with this Yep, okay. What we've done with this example is actually just to acknowledge the possibility that we might not find anything underground. We could find something, 60% chance, or we unfortunately find nothing. Okay, so it's just a probability scenario. Nothing's been said about subsequent decisions that we can make. Okay, so in a more realistic setting, you can imagine that, okay, we undertake this project, and maybe something else then happens that is beyond our control. There may be a possibility that we actually adjust various operational aspects of our project. For example, if you start up a sort of manufacturing project, and if the economy doesn't do well, you have the ability to scale down your operations. And that's indeed the case with a lot of the automobile manufacturers, because when the cars are not selling too well in global financial crisis, they are able to then switch their assembly plants full-time work to part-time work, shut down a few plants and manufacturing, etc., etc. Okay, so those are what we call options to downsize, and there are indeed other options to expand your operation, to scale up your operations if business is good, option to abandon the whole project if things really stuffed up 2 years into the project, and indeed a set of options that we call timing options, the ability to run certain aspects of this project and then pause for 2 years and then continue on. So the ability to defer the operation of the project, things like that. Okay, so these are what we call real options, and real options are just a fanciful name for what I call flexibility, the ability to adjust various aspects of a project given scenarios that are beyond your control. And the example that I can try to give you to try to motivate the value of all these real options, it's not actually to give you an example, but rather to give you a counter example of a project that is inflexible and the destruction or the financial destruction that is actually causing. One of the okay, so keep in mind, okay, I'm not giving you an example of project flexibility, but I'm giving you the reverse, an example of a project that's inflexible and why it becomes very costly later on. And if you can see that, you can begin to appreciate the value of project flexibility. Now, housing, building and construction projects are one of the most inflexible projects. The reason is because you have to do a lot of things upfront to set up this project. You have to auction for the land, pay for the land, get the licenses, get all the construction material, hire the people to then build your office blocks. So you see, construction projects are one of the most inflexible because a lot of the things has to be set up front, and then it's not just that, it takes a number of years before the project is complete. And that's why a lot of the financial crises are often associated with property crisis. The Asian financial crisis is one classic example of commercial property slumps, and indeed with global, not so much global financial crisis, but yeah, you could say that in the US, and indeed in my recent trip to Ireland, in Dublin, it's a banking/housing crisis. So that's what they're experiencing over there. I mean, the hotel where I was staying is, you got this commercial street, our Collins Street, for example. And on one side, you have this new ongoing building project where, you got your first 5 floors of shopping malls, and then the next 20 plus floors of office blocks. It is still in the process of being constructed, and that is actually a very impressive project because what it allows is for the duct system, that is their version of the subway. It's what they call their subway in Dublin. The dart tracks actually run through into the building and out the other way. It doesn't crash, but there's a hole for it to run through the building. So it takes commuters straight into the building, and they can go up to their office once it's completed. So that's on one side of the street. And on the other side of the street, you have the whole row of existing office buildings and office blocks. Older, smaller, but nevertheless. And every third office block has in front of it for sale to let. Every third office block on one side. And you have this commercial project that's in the process of being built that nobody's going to use on the other side. But you can't just leave it there, because all the things are set and ready to go. You can't delay that project. So you see, that's why construction projects are very dangerous, because the decision on a positive NPV project was made in 2007. That's during the boom time. And so 2 years later, while it is almost complete, everything goes to the opposite side. So they're stuck with this nice, fancy building that nobody wants. But they still have to build it. Or else if they just leave it there, all the things are going to go to waste. Okay, so that's why all this project flexibility are actually quite important in terms of factoring them into NPV analysis. Okay. Examples: the ability to downsize or abandon everything in the onset of a financial crisis, and on the other side of the coin, the ability to scale up, to expand our production scale if we have a good, successful marketing campaign, or if the economy becomes good, we have the ability to increase the scale of our operation, etc., etc. So these are what the practitioners like to call real options, but they are nothing more than just project flexibility. And decision trees are often used to incorporate the value of such embedded flexibility in NPV analysis. Okay? So that's the idea of what we're trying to do in terms of decision tree analysis. So it is a common way of drawing things to try to, first of all, make the NPV analysis more realistic. We look at different states of the world, and we attach the relevant cash flows for those different states. So it's a bit different from just sensitivity analysis. Okay? We're actually looking at different states of the world and incorporating the relevant estimates corresponding to each of those different states. So the easiest way of giving you examples of states would be, good state of the world, normal, and then bad state of the world. Good economy, normal economy, bad economy, those sort of things. Okay? And with decision tree analysis, it is very useful to analyze sequential decisions over time. Because you see, with project, back to this example that we've just gone through, there's only one decision. Not do anything, or let's try to do something and see what happens. But whatever happens from this point onwards, there's no more decision to make. It's all up to Providence to decide whether or not we do find something or we don't find anything underground. Okay? But there are other projects whereby you could actually make a decision later on, depending on what happens in the first few years of your operation. Okay? So that's an example of sequential decisions. And we attach the probability values to the different states of the world with different estimates correspondingly. So that's what I've said. But the valuing of flexibility in terms of sequential decisions is what decision tree allows us to do. And that's indeed the example 2 that I'm trying to show you, or to go through with you, hopefully, by the end of today's workshop. Now, that last statement is important, and I think it motivates the importance of looking at sequential decisions. We need to address sequential decisions by going back to front. Now, what do I mean by back to front? Is it discounting back to front? No, not really. If you have a look at this diagram, I don't want to play around with the equipment, so I'll leave it at here. Hopefully most of you would have printed this out. I put it up 2 weeks ago. Okay, so this is the diagram that I wouldn't bother drawing, but it's for example 2. Example 2 is a large plant, small plant that we're going to look at soon enough. Okay, nested decision tree in one of our later slides. But I just want to use the structure of this picture to show you what do I mean by sequential decisions. Okay, now there's 2 decisions, and when we go to example 2, I'll fill in the descriptions soon enough. Okay, so that's not a problem. But just as a preview, The first decision is whether or not to choose the scale of your operation, whether you want to build a large plant or a large factory or to go a small factory. Now, if you do decide to build a small factory, after the first 2 years of operation, if demand is good, you have a further decision to make with your small factory scale. That's the real option, the ability for you to expand your operation. That's what number 2 is for. You have to then decide, okay, if business in the first 2 years is good, is it worth our while expanding? So that's what number 2 is for. And that's a decision we have to make, whether or not to continue with the small scale operation or whether we expand the scale of our operation at the end of year 2. Now, what I mean by sequential decision is indeed the following. You cannot decide on number 1 without first making a decision on number 2. Why? Because to decide on number 1, you need numbers coming from here, and you do not know what number to do here because you need, before you first make a decision on what to do for number 2. The decision you make for number 2 affects the set of numbers you use going back to number 1. And that's why you need to decide on number 2 first, use the relevant set of numbers to then be able to decide, should I go large or small? That's what I mean by sequential decisions. Okay, your decision on 1 is affected by your decision on 2. And you can then imagine, okay, if it's an even longer scale comprehensive project, you would then have your decision on 2 is affected by 3, and then 3 is affected by 4, and so on and so forth. So on Sunday, my wife and I went to watch, Leonardo DiCaprio's new movie. But geez, I can't remember the last time I actually need to concentrate in the movie. It has sequential decisions up to, okay, I won't do the spoiler, okay, but it's sort of like nested decisions, but multiple layers. So I actually have to concentrate on for that movie. And when I walk out, there's a group of youngsters who say, what the heck was the whole movie about? So it's very, I think it's the first time I actually sit and, what is it? And then I have to chat with my wife and exchange notes, or else we couldn't keep up with the plot, okay? So if you're bored with all this, I encourage you to watch that, okay? It's very confusing, to say the least. Okay. But that's what I mean by sequential decisions, okay? And we need to go back to front. That's basically what it's all about, okay? So let's, because of time, you see, the only reason why I gave this example is because when I taught, I remember a few years ago when I taught this for the first time, some students were confused. They were asking me, how can you attach a probability to a cash flow? What are you doing there? So they don't know how to get weighted average cash flows. So that's why I have example 1 to show you that, since it's here, I better do it properly. You see, you take, example 1 is very simple. It's a 1-year project. So you got, you're faced with whether to expand locally or whether to expand overseas. So you got 2 different initial outlays, and then you got probability of success, local and foreign, etc., etc. And you have the corresponding cash flows. I guess the key that I wanted to show students with this first simple example, see, this is a 1-year project, so the calculation is very trivial. But I guess the only thing I want to show students here, I would say hopefully the minority of students, is that to work out the expected cash flow of the 2 different states is simply to apply the probability of that state happening by the corresponding cash flow, okay? So you see, for the overseas expansion, if it's a success, it's 10 million. If it's a failure, you only get 2 million expected net cash flow. The probability of success is 0.3 or 30%. The probability of failure is 0.7, 70%. So your expected cash flow between the 2 states is simply just the probability multiplied by the expected cash flow. So 0.3 times 10 plus 0.7 times 2, that's all. So it's a probability weighted average expected cash flow of the 2 scenarios. That's all. Now, very quickly, if it's a simple average, focus on the overseas project. Okay, so if it's a success, 10 million, failure, 2 million. Simple average, simply, how much? What will be the simple average of the 2? It's just 6 million. Well, 6 million is basically the same as, okay, the chance of success and failure are 50-50. So half times 10, half times 2 gives you 6 million as well. Okay? And so if the probability associated with one state is heavier than the other, your answer will skew towards that number. But whatever it is, your weighted average must be a number that is trapped between the two relevant numbers. So in this case, I don't care what the probability values are. If the payoff for one state is 10, if the payoff of the other state is 2, your answer must be somewhere between those two numbers, depending on the weights. You cannot have 10 and 2 and your answer is negative 4.5 million. Okay, that means it's completely nonsense. 4.4. You mean when you work through the yeah, but then when you divide by 1.1, you end up with this answer. Yeah, yeah. It is 4.4. Now 4.4 is slightly less than the midpoint. The midpoint is 6. Now the answer is 4.4, and I expect the answer to be less than 6 because the probability of failure is heavier. It's a 70% chance of failure. So that's why your final answer of 4.4, thanks to your classmate, is less than the midpoint. The midpoint is 6, but because the failure is heavier, 0.7, so your answer tilts lower than 6 million. Okay? But that's how we work out expected cash flow. Okay, very straightforward. If you still don't understand, then you have to see me after class. Okay, so this is just the insurance policy for the hopefully just a handful of students. Now this is the one that I wanted to look at. Okay, so back to this example. So if you okay, this is quite important. If you, for whatever reason, didn't print this out with you, quickly take out a piece of paper and quickly scribble the rough shape of this picture. Okay. Now, as you are drawing this, those of you who have printed this out, you can start to decorate this picture. Write simple wordings, simple numbers, and also try to incorporate the details on this slide and also for the next slide as well. Okay, try to decorate this picture with numbers and descriptions. If you haven't, then quickly draw out this picture first. Okay, and I'll stress this point. Okay, the most important part of this diagram, if you ask me, is the following. Okay, 0, 2, and 10. So there's 2 cash flows here, and there's a total of 8 cash flows here. Okay. To me, this is the most important, because this tells you exactly what to do, how many cash flows to shift, and how far back to shift them. Okay. So this is considerably easier than the previous example, I think, because in the previous example it's 0 to 2, 2 to 7, and then 7 to 22. This is much easier. Okay. Now, given the the specific details here, if we read from this set of details, it must be the case that, okay, my decision at the beginning, in the onset, is to decide whether to build a large factory, a large plant, or a small plant, or a small factory. Now, the large factory part has to correspond to the top half of this picture, because the option to be able to expand, or decision on whether or not to expand, correspond to the small plant. So that's why if I put another decision here, then this part of the diagram must correspond to the small scale operation. So the top half is large, the bottom half is small. Okay, so I already know that, and I'm able to write down number descriptions corresponding to that. Large, small, big, small, doesn't matter. Okay, you can use whatever language you like. And also, I'm also able to work out, write out what's the initial outlay. Okay, so for the large scale operation is 2 million. And for the small scale operation is 1 million. Okay, so far so good. Now, if I do decide to expand, now see the two paths are similar. So you can choose whether you want expand for the top or bottom, doesn't really matter, okay? So I'll use expand for the top and don't expand for the bottom, okay? So you can write notes for yourself in terms of the corresponding to the 2 alternative decisions for number 2. If I do decide to expand, it will cost me an additional expansion fee of 1.25 million. It If I decide not to expand, then life goes on as usual. Okay, so that part is easy. What other details can we begin to throw and decorate into this picture? Okay. Now, for either case, whether or not we have high demand or low demand is not affected by our choice of whether we go big or small. It is affected by something else, okay, something that's beyond our control. So the probability of initial high demand is 0.8, so I'm able to write 0.8 here. Okay. Probability of success is 0.8, probability of failure is 0.2. Okay, there's only two possibilities, yes or no. Now, if it's a success after 2 years, if initial demand for the first 2 years is high, and then the chance of having high demand after 2 years for the remaining 8 years is 0.75. So if initial success is high, then success continuing on for the remaining 8 years is 3/4. And if it's a success, if it's a high demand followed by low demand, for the remaining 8 years is 1/4. Okay? So what I would write for these two lines here would be 3/4, continuing on for the next 8 years for high demand, and 1/4 if initial demand is high for the first 2 years, it could turn low, and there's a 1/4 chance of that happening. Okay? If it starts low, it stays low all the way. Okay? So 0.2 continues all the way here. Okay? So there's nothing to worry about there. So once you fill in these scenarios for the large plant version, then the small is similar, because the scenarios don't change. Okay, so it is still 3/4 and 1/4. 3/4 continuing high demand, 1/4 high demand becomes low demand. Whether or not you decide to expand, it doesn't really matter whether you decide to expand or not. They're still the same. It's the same as the scenario with the large plant. Okay, so it is this set of numbers here. And the only last thing we need to do is to simply work out the cash flows. And the cash flows are on the next page. And I guess the most common mistake that students make would be to plug in the wrong numbers for the wrong scenarios. Okay, so let's make sure we fill in the numbers accurately. So for large plant, if it's a high demand, it's 0.8 million. Okay. Now, if it's low demand, it's 0.1 million. For the small plant operation, if it's the expanded version, now if it's high demand, it's 0.5. But if it's low demand, 0.075 million. Okay. If we don't expand, then it's just the middle set of numbers, 0.4 million and 0.35 million. And indeed, if you go down this path, it means you're not expanding and demand is low, so it is still 0.35 million here. Okay? So, I mean, these are all the details that we need to use to label this diagram. And once we got this, it's just, the same as before, doing all the calculations and pull all the cash flows back to front, back to front, back to front. Okay? Now, this picture is comprehensive because it covers both large and small. And indeed, it covers the secondary decision as well here. So that's why in terms of the calculation, it seems that there's a lot that we need to do. But indeed, if you try to use the picture, always keep this in mind, okay? Use the picture to guide you in your calculation. It is quite manageable, okay? You must believe that it is quite manageable, okay? So let's look at the two sets of decisions that we need to make here. Large or small, okay? So that's number one. But we can't decide on number one until we decide on this. Should we expand or should we not expand? Okay, we should we need to analyze this decision first because it affects our number one. So what is our decision on, how do we make our decision on whether we expand or don't expand? Okay, so always have the picture in front of you. So we're trying to work out the NPV of expand. If I do expand, it would cost me an initial outlay of $1.25 million, and the expected net cash flow for the remaining 8 years is just 3/4 multiplied by 0.5 plus 1/4 multiplied by 0.075. So that's what I've done here. But this is only to work out the expected cash flow between the two scenarios. There's 8 of them. So I need to apply the annuity to scale back the fact that there's 8 sets of cash flows. So the remaining part of this calculation is simply so when we multiply everything by the annuity formula for a set of 8 cash flows at an overall cost of capital of 9%, this completes the calculation. Okay. So this will give us the NPV of the worth if we do expand. And just as a quick check here, because we've done it before, this gives you a number. Where? Where would that number be? Where would that number be? If I ask you to point.